Hello everyone. So far we've seen a lot of topics around large language models, and by now I think most of you or all of you would be convinced that large language models are really good at understanding language and generating language in a way that was never seen before, right? And in fact, they achieve superhuman performance in a lot of these traditional NLP benchmarks. So now we are going to jump towards a place or a topic where LLMs are not that great at, and people are trying to make them better. As humans, right from our young age, we've been taught how to use tools in addition to our critical thinking, right? So if you know how to, when our math teacher teaches how to solve mathematical problems, they also allow us to use calculators, right? And for logarithms, log tables and whatnot, right? So we had a lot of tools to work with, and so whenever we felt that using tools might be easier rather than making it difficult, we ended up using tools. And then wherever we require critical thinking, we ended up doing critical thinking, right? So that's the part that we're going to talk about now, where we are going to teach LLMs how to use tools and how can they help improve LLM's ability to do their tasks given that they have access to these tools. So to cover this, I'm going to I've divided the lecture into three parts. In the first part, we'll be talking about, let's say that you are given a bunch of tools like calculator or search engine and things like that, which people typically use in their computer. How can we make them useful to large language models? So basically, you're going to incorporate these tools during the fine-tune process so that the model, you teach the model how to use certain specific tools and they end up leveraging them, right? That's the topic that we're going to cover in today's class. In the next lecture, we are going to talk about how LLMs can be taught to use any APIs, right? So there are so many APIs out there for searching flights, for booking flights, for transferring money. There are so many APIs that are available out there that most of us use every day using apps. But if you have those APIs exposed and you have them available to LLMs, can they leverage it and get things done for you, right? So that is going to be the topic that we're going to cover in the next lecture. And the lecture on Saturday, we would be going one step ahead and then see if you have a very complex task. Like for example, if you have to do a flight booking now, right? What would you typically do? You would go to one of these aggregators like Google Flights or Make My Trip or Booking.com, search for your flights, provide your specifications in those facets, search, figure out the flights. You will have certain objective in your head, like you want you want to leave at this time, or you want to arrive at that time, or you want it to be the cheapest. So you have a lot of these objectives in your mind. You express it using the tools and the widgets that are available, figure out what you want, go through the list, and then finally book the flight, right? So now in this, you end up using only one tool mostly, but there are cases where you might have to use multiple tools. Like for example, if you have to create a presentation for a lecture, right? Or a presentation that you want to create for a class, you might be reading through a lot of papers, you will go through blogs, you will have a scratch pad to write things down, and then you will create a lecture and so on. So there are a lot of these complex tasks that are there in our day-to-day lives and also in many enterprise use cases, right? For example, in an enterprise use case, you can think about if you're a software developer and for a certain product, you might have a GitHub repo, and people might raise bugs, and you'll have to figure out what these bugs are, go through your code, reproduce the issues, figure out what you have to fix, and then finally create a PR, and that gets merged, right? So there are a lot of these complex tasks, and what we're going to see is like, how can we make LLMs solve these complex tasks, right? How do you build such a solution which can solve complex tasks using LLMs and tools together, right? So this is where the most of the current research is headed towards, right? And so the technical terms for these topics are, the first part is called tool augmentation. You provide the tools to the LLMs during the fine-tuning stage, you teach it how to do it, and then the large language models learn how to use these tools. The second one is called function calling. Like most of these LLMs that are currently out there already support function calling. Like you provide it with a list of APIs along with their descriptions, they'll be able to figure out when to use them, how to use them, and how to leverage them in their interaction with you, right? ChatGPT does it, Mixtral does it, and a lot Llama does it, and there are a lot more other IBM's Granite models does that, and there are a lot more other enterprise grade LLMs that can do these. And finally, the last part is called agentic workflows, where the goal here is to build solutions using function calling and tools that you have, right? So you need to figure out how you should plan your task. You need to figure out what tools you will have to leverage. You need to figure out, once I execute this tool, I get back certain result. With this result, should I make what choice should I, or what decision should I make to sort of complete my task? So there's a lot of abstract level thinking in agentic workflows, where you think really like a human in a very collaborative environment, right? Even sometimes you would mimic a web developer. Sometimes you might mimic a project manager. Sometimes you might mimic a tester. So you might have different prompts for each of these steps in your complex task, and you will interact and figure out how to get this done, right? So this is what we're going to cover in the next 3 lectures, including this one. So let's jump into tool augmentation, right? So first, let's discuss what are the limitations and how tools can help solve these limitations. The first one is sort of very obvious, right? When you ask questions to large language models, which are more recent and right after when the large language models were trained, typically large language models give a disclaimer or refrain from answering, or in worst case scenario, they would hallucinate, right? They would give you incorrect answers, which looks really plausible. So in this particular scenario, when I queried Mixtral 8x7 billion model, which was sort of with a query, who is the current president of India, it sort of gave us the previous president, right? But it gives you a disclaimer saying, however, please verify from a reliable source, as this information might have changed after my last update. So even though this disclaimer helps us not to trust the answer, but eventually it doesn't solve the purpose, right? You anyway have to do outside LLMs to get this task done. So this is one of the big issue, and what would we do as humans, right? The obvious thing that we would do is that we would use a search engine and then go fire the same query there, go through a bunch of the documents that are present, figure out which document talks about the current president of India, and verify it using the contextual information present in that particular web page. So that's why you see here that the latest version of GPT 4.0, when we use the ChatGPT interface, you ask the question like, say, who is the current Prime Minister of India? It's able to actually do all these steps by first searching this particular query using Bing search, and then it was able to browse through 2 websites, collect enough evidence, and then provide a very elaborate and correct answer. So the interesting part to see here is that here it has ended up using 2 tools, right? One is it has used the search engine. Secondly, it has also used a calendar, right? It knows that when you say who is the current Prime Minister of India, it also added October 2024 to it to make the query contextual, and which means like it has access to the calendar. It can say like, give me today, and that sort of gives you that today's date, month, year, whichever is necessary for this particular query, and then it goes to the web pages and figures out how to respond back. So this is a good example of how when tools are given to LLMs, that they would prove to be a lot more useful. And the second issue is that in general, there are a lot of these expertise that LLMs lack, right? One such big expertise is making precise mathematical calculations, right? So even though models are getting better and better day by day, but they are not perfect. For example, here, this is the Llama 2 13 billion chat model. When I ask a simple question which says that what is the product of these 2 numbers, where one is a really, really large number and the other is a single digit number, the model gives us an answer that is sort of like 2 orders of magnitude higher than what the expected answer is. Even though most of the digits seem correct, but it just added another 30 at the end and sort of made it completely incorrect. So imagine using this for transferring money, right? Like you might end up bankrupting yourself or going into negative balance if it makes silly mistakes like these. So, but obviously it looks like the easiest thing to do is to sort of leverage a calculator, right? Even if you use this in your Google search, it sort of leverages a calculator and gives you the right results. So LLM should be able to do that, right? So so if you see again the latest version of ChatGPT, if you provide a query that requires mathematical calculation, specifically precise mathematical calculation, it would be able to figure out that these are the two numbers involved, and it would be able to give you the precise number. In addition to this, it gives you this tooltip, right? And if you click on the tooltip, it gives you what Python code it generated, right, in order to come up with this answer. So basically what it has done is it has the ability to use the Python interpreter. It created a code in Python, it executed it, got the results back, and it used the results to formulate the response, which seems like the right thing to do at this point in time, right? Because LLMs in general may not be able to do precise mathematical calculations, and calculators can do it quite easily. So it looks like the obvious thing to do, given that you have a calculator at your disposal. So now in this lecture, what we are going to see is how did ChatGPT get to this point, right? How was it trained to sort of use web search engine as a tool? How was it trained sort of to use Python interpreter as a tool? And this sort of happened progressively, and we'll go over how this field sort of evolved over time, right? So the first people who came up with this particular idea of augmenting tools was also OpenAI, where they wrote technical reports about how can we solve math word problems using large language models, right? And we're going to first talk about that, just because that was one of the first papers of the kind, to understand what intuitions they had, how did they define this research problem, and how did they end up solving it, and what lessons people learned, and which helped the field move forward. And then we are going to talk about three important research papers in this particular domain. One is called Tool Augmented Language Models, the other is a Program Aided Language Models, and the last one is Toolformer. All these are progressively making it better, right? And they were like sort of like unique papers in that stand, because they created something that changed the direction of research at each step, right? And finally we'll talk about WebGPT. Again, this is from OpenAI, which sort of which will help us understand how ChatGPT uses web search as a tool, right? So we'll go into details of what is the likely way OpenAI might have used to incorporate web search into ChatGPT. So let's talk about the GSM 8K and the paper that described this, right? So the main contribution of this paper was they created a very simple grade school math word problems data set. It had around 8K question answer pairs, and hence the name GSM 8K. And this is how the problem and the solution look like, right? The problems are typically very simple, where a grade school student can solve this. For example, here it says Beth bakes 2 dozen batches of cookies in a week. If these cookies are shared among 16 people equally, how many cookies does each person consume, right? So this feels like a very simple question, and most of these large language models achieve superhuman performance in many NLP tasks, right? So the goal here was to see how would they perform on a task like this. And so they also used humans to create solutions for these, rather than just giving out the final answer. Humans were asked to solve it step by step as how a grade school student would solve it. Like, first write a natural language sentence that describes what is the first step, and then do the intermediate calculation, and then next step, the next intermediate calculation, next step, and finally the final equation, which gives you the answer. So when the data set was created, this annotation was not present in the data set. This was sort of created post collecting the data set in an automated manner. But when they fine-tuned GPT 175 billion model, right, what they found was the performance was so bad, right? It was less than 30. In fact, it was much less than 30, right? And for a large language model that achieves superhuman performance on squad and summarization, things like that, less than 20% on grade school math seems like a big issue, right? So to move forward in this domain, it's very essential that we at least solve problems like these, before going to solving much more complex problems. So what they did was that they decided to augment the data set with tool calls, right? That was their first solution. So they used an automated way to ingest possible calculator annotations before any calculations were made, right? So while they were not able to annotate every step in the solution, they annotated a good amount of them, and whatever they annotated was right. So basically it was a high precision system, but it was a low recall system for annotations. So when they knew it was right, and when they didn't know, it's okay, right? So what they did was the most number of places where the model was making a mistake is not when reasoning in natural language, but rather when they have to execute the command and then get the output. So basically they were making mistakes in 4 into 2, they were making mistakes in 12 into 8, right? That was a point of error. So what they decided is like, let's annotate and then let's make the model generate something like this until this equal to sign, right? Like from here till here, and then we'll execute this with a calculator and then see how the model does, right? So that's exactly what they did. So what they did was, when you give this input to LLM, it first generates, after this token it generates a plus, after this token it generates a 10, and once it generates equal to, then they see that if it's preceded by a 2 brackets, and if that is the case, they would take this particular expression, execute it, get the result, like you use the calculator to get the result, and then put it back in your input, close it, and now ask the model to generate, right? So this way you never go wrong with this particular expression. So this was the first use of tools while fine-tuning an LLM, and what they did was that they figured out that once you have a data in natural language, figure out a place wherein you can insert tool annotations. So this is called tool annotations, and execute the tool, right? Don't make LLMs do the job for you. If you have a tool that is always going to be deterministic and correct, use the tool to execute it, and once you have the execution results, feed them back and continue whatever you are doing, right? So this was the main idea. But even with that, right, even with that calculator annotations, when you use 8,000 training examples on 175 billion GPT model, it was just able to achieve slightly above 30, right? Again, this was shocking for people, right? This much spoon feeding, still the model is not able to pick up. So one insight they had was that they, rather than doing greedy decode or very high probable, just picking one high probable completion and then using it to represent answer, they sampled a lot with slightly higher temperature. They sampled a lot and they found that some of these answers were right? So while even with providing tools to the LLMs, they were making mistakes here and there, and when they sampled, let's say 100, 5 or 6 of them turned out to be right? So the next idea they came up with was, let's sample a lot, right? Let's sample a lot, and then let's use a verifier to decide which one should I choose. Like sort of score each sample candidate, whichever candidate gets the highest score, let's pick that. So that's what they refer to as a verifier. So what they did was, once you have trained model, you give the question, and so giving the question and the solution helps you train the LLM, right? Let's say you have a GPT-3 175 billion model, you have your GSM 8K QA pairs, right? S is the solution here, and you give both, and then you train the model to generate solutions. So now you have trained the model. Now post training, you ask the model to generate multiple solutions. So you provide the question, you ask the trained model to generate multiple solutions. Here they're generating 100 solutions, right? And once you have the solution, you will be able to get the answer for each. So once you have the answer, check whether this answer is right or wrong. So you will know, so you will get Q, S, Y tuples, and you will get 100 tuples per example. You have 8K examples. Let's say you use 6K for training. So you end up having 6K cross 100 examples to train a verifier. The verifier is also a GPT 175 billion model. They provide this as an input, and just like how BERT has a classifier head on top for classification tasks, you take the GPT, the final token representation of the autoregressive model, remove the output projection matrix, put in your classifier head, and then train it to just say whether this is right or wrong solution. Right? That's all you have to do. So obviously, if you train a classification head, you're going to get probability. And if you sample during inference, if you sample 100 different solutions, you run the verifier on 100 different solutions. For each solution, you would get a score between 0 and 1. And all you have to do is pick the highest, the solution with the highest score. And what they found is that even when you're using 1000 data points, you start to see like good jump in the performance. So from 30%, slightly above 30%, they were able to boost the performance till 55, 56 by using the verifier. So this was the first work that was done to showcase tool augmentation, and the two insights that sort of came out from this paper is that using tools will help you improve your performance on certain specific tasks, and it may be if you have less data, then think of using verifiers rather than just fine-tuning the model. These are the two insights, but the insight that sort of got picked up heavily was the first one, which is if you have a certain specific task at hand and you want to fine-tune the model, and if you think that there is a scope for using tools, then go ahead and use tools. Create tool annotations and use tools. Now, of course, this is going to be an extremely expensive process, right? First of all, collecting training data itself is a nightmare, right? Now, to train a big model, you need like hundreds and thousands of training data points. And now on top of that, they are saying that you need to create tool annotations, figure out how to use tool, where to use tool, and then put them into your examples and then learn them, right? So let's see how the community moved ahead with this. So the next work that we're going to talk about is tool augmented language models. So what they did here is that they just took the abstract idea in the GSM 8K verifier paper, and they said that look, I'm going to have certain special tokens in my LLM response generation, in my LLM vocabulary. One such token is simply going to say make a tool call and give the name of the tool, and then it's going to generate the parameters necessary to call that function, and then I'll say run the tool. So once I give you the token run the tool, then you know how to use the tool, execute, get the results back, again put it back into the prompt saying this is the result that I got back, then I'll continue generating the response, right? There's nothing new. It's exactly same as what GSM 8K people did. It's just that they are going to use it for a lot more than one particular application, right? So like you remember the two limitations that we talked about, right? One was augmenting with search engine, and two was using calculator and other tools. So what they did here was that they ended up using web search for questions that require, for mostly common sense questions or more factoid questions. So there is a data set called natural questions where there is a question and a factoid answer. It can be like a few words. The answer could be few words. And one obvious solution is that you let the large language model answer from its parametric knowledge. That's one way to go about. But these are slightly more involved, like it has to remember dates, it has to remember certain names of people which are not very frequent, which may end up failing. So typically having access to a web search widget here would sort of help it get better accuracies, right? So here the way in which they created the data is that you have the question and then followed by it you give annotations for what tool to use. Here they use search, and here this is the search query, and then you generate this token result. Once you generate result token, then we are supposed to call the web search widget with this query, get the results, put it back, and then add output token there, and the model starts generating the output, right? And similarly for mathematical related QA, they created a certain tool for calculator, and they also define some syntax about how to use calculators, and then design this data set. Again, the important part to see here is that you have to create this data set to begin with, which is a pain, right? It's going to take forever to define how to define this particular abstraction. It has to have divide, and then it has to follow this particular protocol, and then you have to tell this to your annotators. They should do this, make sure that it results in the right answer, and you might have to, the amount of training data you might need would depend on how complex the task is and how naive the LLM is. If you use a weak LLM, you might need a lot more annotations. If you use a strong LLM, you might need slightly less. But similarly, teaching a model how to search, you might not need that many data points. But teaching a model to figure out divide, add, other mathematical operations, you might have to give it a lot more examples, right? Because it has a lot more parameters and it's slightly more complex. So what these guys said was that while the OpenAI paper said that you need to annotate your entire training data with these tools, what these guys said is, you give me a small set to start with, the algorithm will automatically self-play, create more annotations and improve itself. That's what they said. So even though you have capital T data points in your data sets to begin with, you annotate only capital D, where D is much smaller than T. Right? So what they say is, in addition to your input and output, give me the tool annotation, give me the result of the tool execution along with the input and output. So this is going to be your input to your model in addition to your training data, the tool use set and the task set. Basically what they are saying is that you first fine tune a model using this tool use set, because that's what you have to begin with. Once you have fine tuned the model, then the likelihood of it generating correct answers becomes slightly more than the base model. So now run your algorithm on all your data points, and on whichever data point you're able to generate the correct answer, add them into the tool use set again, right? And keep repeating this process, and that's exactly what this algorithm does. So the only improvement here compared to the previous approach was that you don't need to provide annotations on all your set, only a subset, and you can use this algorithm to get to where you want. And they show that on Math QA, using their approach gives you considerable jump from 20 to 50 on even a smaller model, and it sort of looks like even on a 3 billion model, it gives, the jump is almost the same, but there's a good jump. Now, like I said before, for NQ, which is just simply teaching it how to use such tool, you just needed 150 demonstrations because the task is simple. Like, although 150 also seems excessive from a human standpoint, right? If you have Google and you're teaching humans how to use Google, 150 also seems excessive, right? Maybe 2 or 3 searches, they should be able to figure that out. And for Math QA also, they had to use around 2,000 examples to sort of get to a model that fine-tuned reasonably, which also seems very excessive. So that was the biggest issue with this particular model. So in this model, we know how to augment tools. So this was a useful insight. In this, the next paper, TALM, they figured out that you can generalize it to any tools you want, but it requires slightly lesser human annotation. But at the same time, it cannot generalize. Like, for example, you've taught the use of tool in a very specific setup. And if you slightly change the setup, like for example, let's say that you want to create summary, right? Or you want to chit chat rather than just doing Q&A, then the model probably may not be able to use search engine during the chat that you have, right? So that was the biggest disadvantage, that it cannot generalize. Now, the next approach is called the program aided language models. So here, the main crux is that if you have Python interpreters with you, then let's use them. That's what the main sell here. Well, in the previous setting, people just use calculator, right? So calculator has limitations. There's only certain things that you can, certain mathematical operations you can do. Whereas in a Python interpreter, you can do a lot more. right? You can code Python programs to solve symbolic questions. You can write code to solve logical problems. There are a lot more things you can do with program than just with what you could achieve with calculator, and that was the next step. So what they said was that they would create like an in-context learning setup. Like you give let's say here there is again a math word problem question. You create an answer in which you provide a natural language text of what you wish to do, and below that you provide the Python statement of what it means, right? So for all practical purposes, for execution you can consider this as starts with a hash so that it's a Python comment, right? So the interpreter will just ignore it. So what they're saying is Roger started with 5 tennis balls, so they created a Python line that says tennis balls equals 5, and 2 cans of 3 tennis balls each is what he bought. So what he bought is 2 into 3, and how many tennis balls does he have, which would be 5 plus 2 into 3, right? So everything that is explained, rather than expressing it using calculator, you're now expressing it using Python. And all they say is that if you give 5 or 6 such examples, now for any question that you have during inference, you would get its Python program, execute it, and get the output, right? That's all this paper is. So now the good part about this paper is that it doesn't require 150 annotations anymore, because the model already knows Python, right? You don't have to define your own syntax for expressing what that logical form should be. Like it has to have add, divide, it needs to have braces in these places, it needs to use this particular syntax for representing calculation logical form. You don't have to do any of those things, because LLMs are really good at code generation. They know Python very well. So if you just give it few examples, it will be able to pick it up. So this reduced the amount of human effort considerably. And in addition to that, it made it slightly more generalized. So, okay, so this is an example of, like, now if you give a new question, it's able to figure out the reasoning and the Python interpretation of it, and finally when you execute it and print the answer, you'll be able to get the right result. So now this can be extended to a lot more than math related problems. For example, there is another data set in which you have to count, which says that I have a chair, 2 potatoes, a cauliflower, a lettuce head, 2 tables, a cabbage, 2 onions, and 3 fridges. How many vegetables do I have? So here you have to do some sort of logical thinking to figure out which of these are vegetables, and then once you have the vegetables, you just have to add them up, right? So this is the Python code that they gave in the in-context example. Basically, the comment says that I'm not counting the chair, table, and fridge, and then it creates a map with vegetables to count, and then finally you print the right sum, right? So it's not just going to be simple calculator-based math. You can do a lot more. You can do a lot more logical problem solving using this particular setup. So one way where they showed that this is extremely useful is that, of course, they did it on GSM 8K, and during that time, one of the most popular approaches was called chain of thought, right? And I think it's going to be covered in the next class, but most of you might have already know what chain of thought is. It's just that rather than directly predicting the answer, think about what the answer should be, reason, and then print the answer. That's all is a big difference, right? And what they say is if you directly ask Codex, so at that point in time, Codex was OpenAI's code models that did mathematical and logical operations better than the language model. So Codex was the best model at that point in time. So the direct answers were generated using Codex. That only achieved 20% on GSM 8K. And COT on Codex achieved 65. Again, Codex performing the best is sort of obvious at that time. And by using this program-aided language models, it was able to boost up that accuracy from 65 to 70, which doesn't seem that impressive, right? But what they showed is that they created another version of GSM 8K called GSM Hard. So their intuition was that, and again, there was another paper before that said that most of the calculations that were done in GSM 8K were single-digit or double-digit operations, right? And it looks like the LLM has seen so many such calculations during its fine-tuning or pre-training that it knows what these outputs are without actually computing them. So all they said is, I'm going to construct a new data set where I'm going to replace every number with a very high magnitude number, like replace 3 by 32,768, some randomly high number, and once they systematically converted GSM 8K into GSM hard, then there was a huge drop even in chain of thought, which clearly says that the model sort of memorized basic math, single digit or double digit math, and it was not able to scale further. And what these guys prove is that using program aided languages, while there is of course a drop, but it's not as high as what chain of thought or direct had, right? And these are some other existing math related benchmarks, but there's no like new intuitions there that we could not get from GSM 8K or GSM hard. Now, we've moved into a paradigm where you don't need that many human annotations. You just need in-context examples, and the model is able to figure it out. Now, what is the problem again here? The problem again here is that, as we saw in this setup, if you want to solve problems like these, then you need to create a new prompt, right? Because every other question in that data set is very similar to each other. Now, again, the notion of how can we use it in a more generalized setup comes into picture. Like if you're using ChatGPT and you can use a program aided language model setup there. Now a new user question comes and you have to figure out where do I get these in context examples from, or whether the in context examples that I have is going to make sense for this setup or not. And this does not give that much flexibility to sort of incorporate it in a very generic setup, right? So that still was a problem. So that's where Toolformer came into picture, right? This was a very simple but a really good paper, where they said that let's assume that I have access to a certain bunch of commonly used tools. Here they say that they have a QA system, which is an LLM based QA system again, which can answer factoid. You have a search system on top of Wikipedia, right? Because most of the common knowledge is present in Wikipedia is correct and it's trustworthy. So they used a QA system for factoids. They used wiki search. They said that let's use a calculator, let's use calendar, and let's use translation app. Let's assume that all these tools are available to the model during its inference. Now the question is, how do you make use of these tools during your runtime, right? So the LLM has to decide, okay, this is the time I have to use the tools, and now this specific tool should come to help, and I need these arguments to be filled up, and how do I use the output of the tools back into my response generation? So the model has to learn all these things and generalize in a way where if you see something that's unseen during training but still requires the use of this tool, it should still be able to do that job well. That's sort of the goal of Toolformer. So what they said is, they went in the same line of thinking, which is you need to annotate examples which specifically says which APIs to call. Like for example, in this setup, the New England Journal of Medicine is registered trademark off. So it needs to figure out at this point in time, I need to call a QA system. And what I want to call is, I want to call it with this particular question. And once it gives me this answer, I should be able to use that in generating the next steps, right? And same thing goes with the calculator, same thing goes with translator, and then wiki search as well, right? So these are this is how they wanted a data to be created, so that, so look here, it's not it doesn't look like a math related problem, right? It's not a math word problem. It's just saying that out of 1,400 participants, 400 passed this test, and in bracket they've written 29%. So it looks like at this point in time, to compute 29%, it'll be easier for LLM to sort of use a calculator based on the information that was just provided in the past, and then use the output to predict 29 rather than directly predicting 29 by itself, right? So this is not a typical math word setup, but still they figured out that if you end up modifying your training data in this particular format, then it will be easy for the model to adapt to the use of calculator any place where it is needed, right? Similarly goes for translation. The name derives from La Tortuga, the Spanish word for. So now if somebody could tell us what is the Spanish translation of Tortuga, then it becomes easier for the model, right? And so on and so forth. So if you're going to talk about the Brown Act is California's law, and now you know that you need to know a lot about Brown Act to sort of complete this particular passage. So if you have access to Wikipedia and you have it as a reference, like an open book test, then it's easy for you to fill up the remaining of the thing, right? So this is sort of like what RAG was initially set up for, but here we are saying that if I tell you that you have access to Wikipedia, how can you effectively leverage it? So now the whole crux comes, the main novelty of this paper comes in that how do you end up creating this data? Do we need humans to annotate like a lot of your text corpora with this, which seems impossible, right? So their main contribution was that first is that how can you use tools in a more generic sense, like for example this calculator example will tell you why that is important, and second is how do you come up with this training data without human intervention, right? These are the main two contributions of this paper. So once you have such a data where you have the tool-wise annotations made, then all you need to do is use that text-based data sets and then fine-tune an already existing model. But the main problem comes, how do you end up creating this particular data? So this is the pipeline that they use to create this data. You initially start with any text corpora, right? Here they use CCNet, but you can use any text corpora, and after executing their pipeline, you will end up with an annotated text corpora based on the tools that you have. So they use 5 tools. They're going to annotate the whole corpora with all the tools that they have. Let's look at how they do it. So they create a prompt for each task. So you have 5 tasks. They create a tool. They create a prompt for each of the 5 tasks, 5 tools, and all they say is that your task is to add calls to QA API to a piece of text, and they give a bunch of information about how to format them, and they give a few short examples. So here all they say is Joe Biden was born in Scranton, Pennsylvania. So it should sort of look, after annotations, it should look like Joe Biden was born in QA, where was Joe Biden born? And that answer should be Scranton. And then there should also be that annotation that which state is Scranton in, and then the answer is Pennsylvania, right? So this is what they show as few short example. And of course, when you use this and you run it on this particular example, Pittsburgh is known as the Steel City. It sort of gives you multiple candidates, right? You sample a lot and you get multiple candidates. Now, all of them may not be right? So you may have a lot of noise in that. So you'll have to figure out what are the ones I should pick and what are the ones I should disregard. And that's sort of the rest of the pipeline. So what they say is that for each of the questions that you generated, in which state is Pittsburgh, what are the other names, what other name is Pittsburgh known by, what is the second city in Pennsylvania, you execute them and you end up getting answers for each of them, right? So because you already have the QA tool with you, so you can execute this question using the QA tool, get all the answers. And now this is the important part. What they say is, let's say that you only give with the current language model you have, which is the GPT-J for them, you give this the prefix, which is Pittsburgh is known as, and you compute the negative log likelihood of the remaining completion, which is the Steel City, right? Here it says that negative log likelihood is 2.5. Now what they say is like, I'll also give you another input where I give you the sentence, I give you the generated question without the answer, and now compute the negative log likelihood. Here you get 2.1, right? So basically what these two means, this is like slightly rephrased version of this question, right? So that also gives slightly more information to the system to narrow down what the answer should be, right? Because if you ask the question in 2 different ways, sometimes you are more likely to answer, right? Rather than just asking in a one specific way. So they say that now the minimum of these two is what the model inherently knows, right? The model inherently knows this is the likelihood with which I know this answer. Now all they say is that now if you give the actual answer, how much the likelihood increases or how much the negative likelihood drops, right? So here if the executed result is given and the likelihood drops and the difference is huge, then it's a really good candidate to preserve. And if it gives you a wrong answer, your likelihood will probably shoot up even more than what your negative log likelihood would shoot up even more than what it was before. So in that case, it is a bad example. So this is a simple strategy that they use to create a lot of training data. right? This is just an example for QA system. You could do this for calculator, you could do the same for translator, you could do the same for wiki search, and every other tool that the Toolformer uses. So now what they clearly show is that for a lot of these tasks, most of them are related to each tool that they used, right? So temporal uses calendar, multilingual uses translation, math uses calculator, question answering uses wiki search, and QA plus wiki search. Fact completion also uses QA plus wiki search, whichever is more suitable for the model to work on. And what they see is that when you augment with tools, you see a improvement in GPTJ. This is GPTJ without the Toolformer setup. This is GPTJ with Toolformer setup. In all cases, you see a jump, and in many cases, you see that it's even a 6 billion Toolformer model is even better than GPT-3 175 billion model, right? So like in temporal, it is much better. In multilingual is much better. In math problem solving is much better. We already knew GPT 3.5 was not, GPT-3 was not that great at math. Even the paper in 2001 said that. But still, these guys achieved a lot better numbers. And the only exception being QA, because the question answering data set was based on Wikipedia, right? So GPT-3 knows a lot, like sort of have almost memorized Wikipedia, right? So that's the only sort of task in which Toolformer was not helping as much as it should. But still, if you see the difference between a 6 billion and 1.5 billion model, it's not that bad, right? So now we have come to a point where you need very few annotations per tool, right? You just needed to create that prompt for each tool. You needed probably 5 or 6 examples per tool, and this tool can now generalize to use of this tool in any chat completions, right? It's not specific to a certain way of asking the questions, but it has become so sort of versatile. Now the next step here is that we have reached whatever we could reach with a given set of tools that I can give you. Now the next obvious step is, now if I give you a new tool and describe what this tool can do, can you leverage it and then do tasks related to that tool better, right? That's what we're going to cover in the next lecture, right? So just before we wrap it up, I just wanted to talk about one of the cool work that OpenAI did called WebGPT. This sort of will give you how they ended up solving the search engine related problems in their newer version. Right now we can see that it did a Google Bing search, it went through certain results, it collected evidence, and then it printed out a more coherent answer which uses the web search, right? So this is the setup that they use to create training data for that particular learning. So what they did was they created a UI, right, where you could enter a search query, look at the results, right? Once you click on the result, you will be able to see what all contents are there in the result, and then you could add a quote which basically says that I have a scratch pad and I'm going to say that I'm going to add a new quote for this link, and then I'm going to save this part of the text, right? So that sort of is what a quote is, which can be seen here, right? So they go through the web search result one by one, open a search result, get a small text that would help answer the question at hand, keep it in a scratch pad, then go to the next result. Then once you're convinced that they have enough information to answer, then they stop doing search. Then they take all the quotes that they have and then ask the LLM to generate a response, right? So the good part is that they actually used humans and they gave them this tool and then asked them to do what they would typically do to answer this question, right? So they saved those, then they created an answer using that and things like that. So now with that, they created a training data of this type, where you have the question and you have all the codes that you had saved until this point in time, right? And then you have all the past actions you did, and then you have access to the current set of result page, right? And then you're asking the model to say what is the next action you want to do. The next action could be clicking on a different result. The next action could be like going to a new page. The next action could be, I just want to stop using the search engine and I'll go to the answer generation phase, right? So these were all the list of clicks or different actions a human could do using the tool, and they sort of translate it into natural actions, right? So basically, what you're doing here is you're teaching LLM to exactly mimic human behavior of how a search engine is used to come up with an answer, right? And with this amount of data collected, they were able to train a model, right? Just do simple supervised learning. You have the entire list of commands, the entire sequence of commands that you clicked and what you do, what you quoted, everything you have, right? How you did you scroll up the web page, did you scroll down the web page, what content you saw, what is important. You have all those details. Figure out what action you should do next, and then once you have enough actions, then so this they created training data, supervised training data with this particular logs, and then they did a little bit of rejection sampling, a little bit of reward RLHF in it, and things like that to get to a system. So I'll ignore those. I'll sort of skip through those details for the lack of time. But eventually they got an amazing result based on that. And this was done in early 2020, early 2022, and it sort of was a paper by the same set of, almost the same set of people who did GSM 8K. So they were working on both. So the two big problems that we sort of talked about today were both sort of initially explored by OpenAI, where there is this website called a WebGPT answer viewer, right? So basically, if you, let's say that if you click any questions here, how does fingerprint unlock work, right? So here it says that it sort of gives you the answer, but on the right side, it shows you what all actions did WebGPT take to arrive at the answer. So it'll show you which result, what search query did it use, what link did it click, how did it scroll up, scroll down, what text did it quote to save it in his scratch pad, and then once it has all those quotes saved, then it will generate the final answer, which is shown here along with the citation, right? So this was what initially Perplexity AI was also trying to do, right? Where instead of having a search engine give you just search results, they would use the search results and then create a more aggregated view of all the search results and give you a natural language text to consume. This is exactly that. And here you could see output of different sized model as well with different rejection sampling techniques. So this is a very nice thing to see. And similarly, the program aided language modeling paper that I talked about, they also have a nice website wherein you can see the outputs of different tasks. How did chain of thought work? How did PAL work? It'll give you a more good feel about where it helps and then where it doesn't help. Okay, so to summarize, we started with discussing how people introduce the use of tools in LLMs, and then we talked about how you can create a general framework for using tools but requires a lot of annotations, and then we talked about how you can reduce the number of annotations, but still at that point in time we were not able to generalize to all the settings where these tools can be used. And then finally we talked about Toolformer, which is if you give it a set of tools, it will automatically create labeled data for it, and it will help you use those tools in any context where the tool is necessary, right? And as a bonus, we also covered WebGPT, which is sort of the idea behind how ChatGPT answers current questions, like recent events based questions. All right, thank you.